It is chapter 7. However, there's something we left in chapter 6 that we need to finish. And one experiment has been conducted in this way shown in this diagram. There's a source of electrons, and when they come out, electrons bypassing a small hole right here, pinhole, it forms a beam. As beam travels through the external magnetic field, we find out that electron beams has been split in two. According to physics, it is because of the different way of the spin that the electrons possesses. So for example, electron could spin clockwise, or the electron could spin counterclockwise. As you can see, they have a different north pole. Okay, so north pole will be the different direction. So that is the reason why we would prefer to use an arrow to indicate where the north pole is. So we realize that electron could have two different modes of spinning. And these two different modes will give us another quantum number that is for electron only. We call it spin quantum number m sub s. And there are only two possibilities for electron to spin. In order to show the difference of this particular quantum number, which is about electron and electron only, this time we use fractions instead of a whole number. So we give it negative 1/2 and positive 1/2. When we combine the spin quantum number along with the other three that we have discussed before, we realize there are four quantum numbers. The first three, principal quantum number, angular momentum quantum number, and magnetic quantum number, they are for to identify an atomic orbital. Remember that we say atomic orbital is pretty much like a room in a space for us to find electrons. And the fourth quantum number, as we realized here, is for electron and electron only. So now we understand that we need four quantum numbers to identify an electron. And of course here, as you can see in column functions, we lay out those functions for the three quantum numbers to identify an atomic number. Now, let's start with the hydrogen atom. Because for hydrogen atom, everybody knows there's only one electron. So how are we going to be able to use these four quantum numbers to identify such an electron? Remember, the electron must be in its most stable state, which is ground state, to be stable for a long time. So what is the value of n for the ground state? If you recall, n is about energy levels, right? So the smaller the n, the lower the energy level. And also, the closer electron can be found to the nucleus, the smaller size of atomic orbital. But it is the lowest energy level that we're interested in. For the lowest energy level, n must be the lowest value or smallest value, which is 1. It cannot be 0. So n is the smallest value we can have for n. So once the n has been set as 1, we have no choice to have 0 as the only acceptable quantum number for L. Remember, L must have the value that's less than n, as we discussed in chapter 6. When L is equal to 0, m sub L has to be 0 as well. And for the first electrons, we give it positive 1/2 by default. That's it. That is it for us to identify the only electron in the hydrogen atom with these 4 quantum numbers as a set. What about helium? An atom with 2 electrons. Now we have a question to answer. Is the second electron going to the same atomic orbital, or the atom, so that electron, the second electron of helium, should go to a different atomic orbital? In order to get the answer of this question, we must understand and find the answer for this question. Just how many electrons does an orbital hold? If that orbital holds only 1 electron, then second electron of helium has to go to a different atomic orbital. If the orbital can hold 2 electrons, then second electron should stay in the same atomic orbital as the first electron. It's possible, but will that electron stay in the second orbital? And how? In order to answer such a question, we have to get the Pauli exclusion principle. This principle says no 2 electrons in the same atom can have the same set of quantum numbers. Kind of like in this country, no 2 persons in the United States can have the same set of a social security number. So it makes perfect sense. For each electron, it must have its unique identity. So as we explore the quantum numbers for these 2 electrons of the helium, we understand the first electron is going to be the same as that of hydrogen. We have n equal to 0, 1, L equal to 0, M sub L equal to 0, and with a positive 1/2 spin mode of such an electron. Remember, we have a Pauli exclusion principle in action. So that that principle actually will tell us just where we're going to put our second electron in the helium atom. Where? Can the second electron go into the same atomic orbital as the first electron? Say the second electron will have the same atomic orbital as 1, 0, 0 for those 3 quantum numbers. How can we make the difference according to the Pauli exclusion principle? But how can we make a difference for second electron? Remember, for the spin mode, there is a negative 1/2 for electron. So the second electron could have negative 1/2 as its spin mode. And that will let us know that first conclusion of this Pauli exclusion principle, which is the electron must have its unique identity in an atom. Now, let's try to think a little bit further about this Pauli exclusion principle a little bit. Say, can we add the third electron into the same atomic orbital without having a same set of quantum numbers? Apparently, we can't, right? Because if we add third in, then the third electron must have the same spin mode with one of these 2 electrons, because it's either plus 1/2 or negative 1/2. So that discussion gives the even more powerful conclusion of this Pauli exclusion principle, which is that an atomic orbital can hold the maximum of 2 electrons with opposite spin. In other words, the capacity of an atomic orbital is 2 electrons. Once it has 2 electrons, the spin mode of the electron must be opposite. Remember the arrow, one going up, one going down, so that must be it. From this slide on, we will split the 3 quantum numbers of atomic orbital in 2 groups. M sub L all by itself as one group, and we have N and L combined as a second group. The reason for that is M sub L indicates an atomic orbital, while if we combine N and L together, we will have a definite energy level for a subshell. When L equals to 0, we understand the ladder for such L is S. So the subshell is 1s. From this slide on, we will no longer call N or L anymore. We just say 1s, 2s, 2p, on and on and on for those various subshells. And that indicates the combination of N and L. Remember, when we combine N and L together to define a subshell, the rules for those quantum numbers, especially for N and L, still applies. That means the value of L must be less than that of N. Okay, I just want to point that out before we go in further. All right, we have done helium. Congratulations. Now, our next challenge is what happened if we have a third electron like lithium. That is my favorite element for the obvious reason, as you can possibly guess. So once we have the third electron going in, we understand 1s is full. And for the first principal shell, as we learned from chapter 6, there's only one orbital, 2 electrons. So the third electron must go to the different orbital. Question is there 1p? If we translate p back to the value of L, we realize the value of L is 1. Can we have this situation where L has the same value as N? Of course not. So now we realize that the third electron must go to a second principal shell. Once it's going to the second principal shell, we got the 2 subshells to choose from, 2s or 2p. Which one comes first? Which one should the electron pick? And if you recall the statement about energy we had on the F subshell or the F orbital, we said since the F orbital has 8 lobes, in order to restrain electrons in these 8 lobes, there is going to be some cost. The cost here is energy. That statement actually tells us F orbital has higher energy level. And if we consider S orbital, there's only 1 lobe. In other words, in order for electron to stay in an atomic orbital, there's no extra amount of energy required. From this point, we realize that compare S and F, S has the less amount of energy, or has a lower energy level. S has 1 lobe, F has 8 lobes. What about a P and D? P has 2, D has 4. The more the lobes, the higher the energy that's required to restrain electrons within those lobes. So we suddenly realize we can make the order of those angular momentum quantum numbers. That is, the lower the L, the lower the energy level. Have that been said, we realize between S and P, it is S subshell that electron should go to. All right, let's talk about my favorite element, lithium, Li. The third electron now should go to the second principal shell, and it is going to be 2s for electrons to go to. What is the atomic orbital or the quantum numbers for 2s? N is equal to, for s, L equals to 0, m sub L must be 0. And again, for the same argument, we give plus 1/2 for the first electron occupying such orbital as its spin mode. This is it for lithium. We have 3 sets of quantum numbers for these electrons. They all different, satisfy the Pauli exclusion principle. What about beryllium? As we understand, the first 3 electrons must have the same electron configuration as lithium. The fourth one will stay in orbit of 2s with the opposite spin. That means ms of a fourth electron must be -1/2. And also we can go on the boron, the fifth atom. Fifth element, that means there's going to be 5 electrons. Remember, atom must be charge neutral, right? So atomic number of boron, 5, also indicates the number of electrons of such atom. The first 4 will occupy 1s and 2s and make both orbitals fully filled. Now, the 5th electron has to go to the 2p subshell. There are 3 orbitals labeled as either -1, 0, or +1 for the m sub L. I just choose -1 for arbitrary reason. It could be 0, it could be 1, so you can make a choice. But for me, I just choose -1 as one of the 3 orbitals that accept that electron. And also, we can play this thing on and on, but I think it is worthwhile for us to take a pause here. Because as we going back, as looking at those energies of those subshells, we suddenly realize that 1s always has the lowest energy level. So if we have a first 2 electrons that are going into the atom, the 2 electrons must occupy 1s subshell. And 2s is the next lowest energy level for electron to occupy. And once the 2s being occupied by 2 electrons, remember the case of lithium and boron, so those 2 electrons occupy 2s, then the 5th electron goes to the next energy level. So once we realized it, so we can actually arrange all of these atomic orbital subshells according to their energy level. And as you can see, 1s has the lowest, 2s second lowest, 2p 3 orbitals, I would like to remind you, and this is the third lowest, followed by 3s, 3p, and you start to see that's quite an interesting case here. And 3d and the 4s, they just switch the position. This energy level of this subshells actually leads us another principle we call off-ball principle. In this principle, it states that electrons occupy orbitals starting with the lowest possible energy subshell available. That means if 1s is available, electron always occupies 1s. If 1s is full, and then it's going to occupy the lowest possible energy subshell available, which is possibly 2s. And when we remember filling in electrons into the 1s, 2s, we realize that electrons must occupy all orbitals in a subshell before moving to the next available one. In 1s, 2s, there's only one orbital, so once they fill it up, electrons move on. But we're going to see that later on when we deal with electrons into p subshell. And we have to understand this way in arranging electrons is for the ground state atom only. If we have atoms with excited electron, that electrons could be anywhere in those atomic orbitals. So off-ball principle only applies for the ground atoms. I don't know about you guys, but when we deal with these 4 quantum numbers for each electron, pretty soon we'll get tired of it. So that is why people start to develop another way to understand or to note that very special quantum numbers for those electrons, which is we call it electron configuration. And here I'd like to use a 2p2 as an example. P, as we already understand, that is the letter that's designated for the value of L, the angular momentum quantum number. The coefficient of a 2 in front of a P actually is the principal quantum number. The superscript of that 2 in our symbol here indicates just how many electrons in the subshell. Alright, so for 1s, 2s, we understand there are going to be 2 electrons because capacity of one atomic orbital is 2 electrons. But later on, as we will experience with filling electrons in the subshell with the multiple orbitals, we may need the orbital diagram. So each underscore or the box or the circle, whatever that is, indicate one particular atomic orbital. That means very specific value of m sub L. And remember, Pauli exclusion principle tells us each orbital can hold as many as 2 electrons with the opposite spin. So we can put as many 2 electrons with one arrow up and one with arrow down. That indicates the 2 different spin modes. So that is the electron configuration in orbital diagram. And we're going to see that as we talk about electron configuration for our next element, that is after boron. Boron is number 5 element, carbon is number 6. For carbon, it has 6 electrons. The first 4 will occupy 1s and 2s, no surprise. And the 5th one will have the same electron on quantum numbers, the set of quantum numbers as the 5th of electrons of a boron. The 6th electron will also stay in the 2p subshell. All right, it sounds normal, but there might be some problem. What kind of a problem will that be? Because with the 2 electrons in 3 atomic orbitals, we could have 3 possible arrangements of these 2 electrons in 2p subshell without violating Pauli exclusion principle, as it shows right here. We can have the 2 electrons occupying the same atomic orbital with opposite spin. That is what the Pauli exclusion principle tells us. Or if we can, so we can have 2 electrons occupying different atomic orbital. That makes perfect fine for Pauli exclusion principle, because different orbital will have a different set of quantum number. So each electron will have its unique set of quantum numbers. With these 3 arrangements, which one will be true? We need help from our third rule we call Hund's rule. Hund's rule is very specific for the situation like this. Electron try to fill in a subshell with multiple orbitals like a p, d, and f. In doing so, electron will first occupy each orbital. Kind of like if we have siblings in a house, if there is a room available, each sibling will prefer to have their own room. Electron will do the same, because remember, electrons are negatively charged species. If we got 2 electrons in the same atomic orbital, they're going to repel each other. So from that statement, electron fills the first orbital. Electron fills each orbital first. So that means the first arrangement is gone. And also, if you look at the second statement, electron will have the parallel spins while they occupy the different orbital. The parallel spin, that means the both arrow either pointing up or pointing down. So that kicks away our second arrangement, because we got a different spin mode with these 2 electrons. So the third one actually is good according to Hund's rule. We got the 2 electrons occupying the different atomic orbital of 2p subshell with a parallel spin. Meaning, if you want to put an arrow, the arrow must be both up or both down. That's what the Hund's rule is. And I'd like to remind you, Hund's rule is very important. Everybody understands about the Aufbau principle. We just fill up the orbital. Okay, we just fill up the orbital from the lowest to the highest. And for Pauli exclusion principle, 2 electrons per orbital. But Hund's rule will tell us what we're going to do if we have electron occupying the multiple orbitals. So Hund's rule actually is more important to our course than the other two. Let's go back, because boron is the first element that we see electron occupying the piece of shell. Actually, it's two pieces of shell. According to the electron configuration, we realize that we got two subshells having electrons. And those two subshells are in the second principal shell, because there's 2s and 2p. And remember, the greater the n, the outer the principal shell it is. So if we add up these two electrons in its two subshells together, we find out that there's going to be 3 electrons. And those electrons must be found in outermost shell, the shell with the highest n. 2 plus 1, that's 3. If you have a periodic table nearby, I would like you guys to check out what is the group number of a boron in this periodic table. It's 3a. 3a, 3 valence electrons, because valence electrons are the electrons in outermost shell, the shell with the highest n. Would that be the coincidence? 3, 3. 3 valence electrons in an atom that belongs in the group 3a. Well, let's check that out with carbon. For carbon, again, we find out that there are a total 4 valence electrons, because I got 2 electrons in 2s, 2 electrons in 2p. Both are in the second principal shell, which is outmost. And I'd like to remind you the group number of carbon is 4a. Still not convinced? Let's try the nitrogen. Nitrogen has 7 electrons in total. The electron configuration tells us it's 1s2, 2s2, 2p3. By the way, I'd like you guys to think about what is the capacity for this subshell of 2p in terms of electrons. 3 orbitals with 2 electrons in each orbital. Total number of electrons must be 6. So 6 is the capacity of electrons in the p subshell. As we try to put the third electron in the 2p subshell, according to Hund's rule, it must occupy the last empty 2p orbital with parallel spin. In the case of nitrogen, now we understand nitrogen atom has 3 unpaired electrons. Those unpaired electrons actually is quite unique, because it will result some unique magnetic property for those atoms. And we can use those atoms for our MRI. And of course, nitrogen is not the best choice, and we have some other better choice for taking MRI. The atoms with the more unpaired electrons within. Speaking of valence electrons, as we add 2 and 3 all together from 2s and 2p, there are 5 valence electrons, and the group number of nitrogen 5a. So that we know for certain, the group number actually tells us just how many valence electrons an atom can have. What is the valence electron? Again, It is the electron in outmost shell, the shell with the highest end. It could be multiple subshell in this case. Now let's look at oxygen. Oxygen now has the 4 2p electrons. Remember, according to the Hund's rule, the first 3 electrons will occupy the 3 2p orbitals. Where should the fourth electron go? Since there's no more atomic orbital that's available for this electron got no choice but pairing with one of the electrons in the orbital. And oxygen has 6 valence electrons, as you already see. Fluorine, number 9 element, 9 electrons in total. Electron configuration would be 1s2, 2s2, 2p5. And the 5th 2p electron will get a pair with another electron in an orbital. That leaves out only one unpaired electron in a 2p subshell. 2s2 to p5 makes the valence electron 7. That number of electrons, 7 valence electrons. And I'd like to remind you, fluorine is in the group 7. And finally, neon. And we realize that according to the orbital diagram, all the orbitals are full filled, are filled in full. So that is the reason why neon does not have too much of a chemical activity, because neon does not need extra electron because it is perfectly fine with the electrons that it has now, and neon does not want to lose any electron either, because all the orbitals are occupied by 2 electrons. That is the perfect condition for neon as an atom. And as we see the valence electron, there will be 8. And everybody knows neon is an element in the group 8A. So from the electron configuration combined with the orbital diagram, now we have pretty good understanding about why fluorine is extremely chemical active. Because fluorine is just 1 electron shy to have the same electron configuration as neon. In other words, fluorine will do anything to grab that 1 extra electron. This is some thinking that we can have when we look at those electron configurations of fluorine and neon. As we move on to the 3rd period of this periodic table, we have another 8 elements, from sodium number 11 element all the way to argon number 18 element. And the story is going to be pretty much the same when we fill in those electrons into the subshells, because we have finished the 2nd principal shell, because that principal shell should have 4 orbitals, n squared if you recall. So 4 orbitals with 8 electrons. Now we need to go on to the 3rd principal shell. And for those elements that are in the 3rd period, I want you guys to think of whether there is going to be the coincidence too. Okay, so from sodium, as we see, the 11th electron will go to 3s, because s has a lower energy level than p, as we already discussed. So with the 4 electron configuration, 1s2, 2s2, 2p6, 3s1, magnesium, 2 electrons paired up in a 3s orbital. For aluminum, just like the boron, okay, that above it, we start to see 1 electron occupying the p subshell. Only this time, it's a 3p instead of 2p. And silicon after carbon, 2 ampere electron. Phosphorus, like nitrogen, 3 ampere electrons according to Horn's rule. And sulfur, chlorine, argon, they are very much like oxygen, fluorine, and neon, as we discuss all those elements in the second period. But when we write up the 4 electron configuration, we start to see how long it becomes. And for every element we got here, from sodium to argon, they all have 1s2, 2s2, 2p6. And which element has such electron configuration? 1s2, 2s2, 2p6? It's neon. That is the reason why we as a chemist prefer to use a noble gas to describe the electron configuration for some electrons that may not be that important in chemistry. And this node of electron configuration is called condensed electron configuration, or noble gas notation for electron configuration. So here we are going to use immediately preceding noble gas by chemical symbol as a core electron. That means if we look at those elements in the third period, we only use neon because neon is immediately preceding noble gas, not a helium. So the rule of this condensed electron configuration tells us we have to use the noble gas element that is at the end of the period that is right above such element. We have just finished the first 18 elements with their electron configurations. And as we put them all together, the hole we have right here, the gap we have right over here, that's for the transition element, which we're going to talk about in a few seconds. As we put them all together, we start to realize there's something common that from this compile of the elements. First, we realize for each period, it starts with NS. What is N going to be? N is going to be the number of the period. So for hydrogen, the N is equal to 1 because hydrogen is in the first period. And the period ends at MP. Of course, helium is the exception. Helium actually should go on top of a beryllium, but we put a helium on top of neon for the obvious reason, because helium is also a noble gas. Doesn't have any chemical reactivity whatsoever. In the case of neon, we realize it's going to stop at MP. Neon is the second period, so N is equal to 2. So neon is the last element in that period with the 6p electrons. That's also true for the sodium and argon in the third period. So now we realize how this periodic table is organized. Start with NS and with NP for the period. For the elements in the same group, same column, they must have the same electron configuration in their outermost shell. So for example, hydrogen. 1s is the outermost shell, it's 1s1. For lithium, outermost shell is a 2s with 1 electron. For sodium, outermost shell is a 3s with 1 electron. Same electron configuration in the outermost shell, indicating similar chemical properties. Because it is that 1 electron that makes lithium, sodium chemically reactive. And then when we look at the elements in group 8A, so we realize we got a full shell, either S all by itself, like 1S, or S and P, fully filled. So they are generally chemically inert. But for the elements in group 7A, there are only 1 electron away to have the same electron configuration as elements in group 8A. So they become highly reactive, trying to gain 1 extra electron. For group 1A element, there are just 1 electron too many, right? Remember that we discussed the situation for sodium or lithium in chapter 2. For lithium, it's either losing 1 electron or gaining 7 electrons to have the same electron configuration as helium or neon. Which one is better? Of course, by losing 1 electron. So the lithium sodium becomes the highly reactive metal by losing that electron, the extra electron. Because after losing 1 electron, lithium will have a helium as its electron configuration as lithium plus. Sodium plus will have neon as its electron configuration. Perfect, right? So they can be stable. From this discussion, suddenly we realize that we can have another way to describe the octet. This rule tells us by losing or gaining in the cases of group 7A and 1A, or sharing electrons, which is we're going to discuss this in chapter 8, atoms must have the same electron configuration as noble gas element to be stable. That is what the real octet rule is for. And I just want you guys to understand, for general chemistry, octet rule is the rule to explain the chemistry of the elements, especially for main group elements. Unless you're in a chemistry major, you won't have much of a chance to contact those transition metals, okay, with their chemical reactivity. So octet rule is the rule to explain the chemistry of the elements in general chemistry as well as organic chemistry. Let's move on to the 4th period. As you may realize, for the 4th period, n is equal to 4. If n equals to 4, in theory, we could have 4 subshells, right? 4s, 4p, 4d, and 4f. And of course, the first two elements, potassium and calcium, will have their electrons occupy 4s subshell. But starting with the number 21 element, the scandium, things are going to become quite interesting. The electron will actually occupy 3d subshell, not 4p subshell. Remember the argument that we had before, 3d by having 4 lobes, okay, so the d orbitals or the d subshell, the orbitals in the d subshell, by having 4 lobes to have those electrons restrained in those lobes, it's going to cost more energy. That is the reason why 3D actually has the higher energy level than 4S. Because of 4 lobes, more electrons is required to have more energy is required to hold those electrons in those 4 lobes of d orbitals. So 3D has a higher energy level than 4S. But once the 4S is fully filled, actually it is 3D comes to the next before 4P. Scandium is the first element that we see electron filled in the 3D subshell. Fine. For titanium, 2 electrons in 5 3D orbitals. Here we need to follow Hund's rule. So there's 2 electrons occupying 2 different 3D orbitals with a parallel spin. Vanadium, same, 3 electrons, 3 different orbitals with a parallel spin. But chromium is something different. Because we notice there's only 1 electron in 4s subshell. And we got 3d subshell half filled. When we say half filled, that means we have 1 electron in every d orbital. Moving on, for manganese Mn, we have electron filled in 4s. So that started to make sense, right? 4s to 3d5, Hund's rule is in action. So we have 5 electrons in 5d orbitals with parallel spins. So as we count, we have 1, 2, 3, 4, 5 ampere electrons. Not the one with the most ampere electrons. As a matter of fact, it is chromium has 6 ampere electrons. Iron, the 6th electron has to be paired with one of the electrons in the 3d orbital. Cobalt got another electron paired. Nickel got a 3rd electron paired. Copper, however, is another interesting thing because, again, we see only 1 electron in 4s. While 3D is completely filled. Zinc, now we have another electron filled in 4s, make both 3D and 4s completely filled. If we move on to the number 31 element, we start to have 1 electron occupying 4p, which is quite similar to the cases like aluminum or boron. And here is the 4 electron configurations for those 10 elements, and these are the condensed electron configurations. And here we use argon as a core, the immediately preceding noble gas. And I want you guys to think about just how many elements we have in this transition block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements. The capacity of a 3D subshell for electrons, 10. It's not a coincidence, because from D1 to D10, each electron configuration will result in an element. So that is the reason why we call the 10 elements layout in transition groups as the 10 groups of these transition elements. The electron configuration for chromium and copper are called anomalies in filling electrons, because according to the Aufbau principle, Pauli exclusion principle, and Hund's rule, what do we expect for chromium to have electron configuration as argon core 4s2 3d4? And there's one orbital that's left empty in 3D subshell. And as you can imagine, one electron 4s orbital sees the opportunity and it jumps into the 3D subshell by occupying that orbital. And that definitely has some kind of a driving force to make it happen. Like by having one electron in each orbital, that will eliminate the repulsion between the electrons while they are in the same atomic orbital. Since the repulsion is gone, the atom or the system becomes more stable. That is probably the reason why it is quite obvious to see that the subshell is heavily filled. Because in this case, in the case of chromium, each electron will have its own atomic orbital. Perfect for the electron. So that is why chromium has the actual argon core 4s135 as its electron configuration. For copper, we just don't see the case here, because even if we have one electron move from 4s to 3d, still we do not have any repulsion eliminated. But why we still have one electron jump from 4s to 3d? And actually the mathematics doesn't tell us that much, but we can come to a conclusion or our observation to say, if we have a D subshell half or completely filled, it will trigger some energy release to make such arrangement more stable in energy. How and why? Nobody knows. Because people just don't care anymore. People just do not want to waste the money to investigate something that is not that so important. Let's go by it. We recognize the pattern, and we can come up with some kind of explanation for some of these. That's good enough for us, and we just simply move on. We can save our money to investigate something even more important. So that is something that people left behind in their research, because it's just like pointless for them to conduct such research to find out why. All right, so after we finished that 18 elements in the fourth period, and we have a pretty good feeling about the elements in the entire periodic table. Now we realize each row from top down indicates the value of n. The first row from the top, n equals to 1. Going down, that will be second, third, fourth, and for the entire periodic table, the n is equal to 7. That's it. Okay. And we're still working on some of the elements in the 7th period. And we do not have any element that is in 8th period, because atoms that in 8th period becomes quite unstable in their nucleus. So they'll cause nuclear decay, and with very short lifespan for those atoms. Sometimes it's just too difficult for us to catch it. In other words, they will be long gone after a billion years of evolution on Earth. When we look at this this periodic table, and we realize we can divide this periodic table in 4 blocks. The most left-hand side, 2 groups of elements is what we call the S block, with the electron configuration NS1, NS2 for their valence shell or the outermost shell. There are 6 groups of elements on the right. We call it as P block elements. This is where we start to see NS2 and P1 all the way up to NS2 and P6 for the electron configuration in the outermost shell. What about the inner shell? The electron configuration of its immediately preceding noble gas. The one right in the middle, there are 10 groups of elements we call as D block elements. And since they're all metals, so we call them transition metals. So from D1 all the way to D10. And I'd like to remind you, 3D first appeared in the 4th period. So when we try to figure out what the n value for D is, it's n minus 1. 3D in the n equals to 4, so 4 minus 1, that just gives us a 3, the coefficient of the D. And 5 minus 1, that is what is see the 4D in the 5th period, so on and so forth. The last 2 rows of elements are what we call F blocks. There are 14 columns. And for F subshell, we understand there's going to be 7 orbitals. 2 times 7, 14. So we can have 14 elements represent those electron arrangement from F1 to F14. For 4F to appear, it has to be the 6th period already. And so that's a 6 minus 2. So we start to see 4F. 4F goes right here. And for 5F, it goes right here. And with that blocks and the n in mind, we can actually write up the electron configuration for any element with this structural feature of this periodic table. For us to start, we always start from the very beginning, hydrogen. Why? Because of Bulk principle. If we have the first 2 electrons that has to go fill in the atomic orbital, it is a 1s. They go. Right. So we're going to begin writing our electron configuration right from here, and then we cross the period to hit the end, and then we're going down starting from the second period on and on and on until we hit the element in the lower position. Let's practice that with this example of nickel. We are trying to write a full electron configuration of a nickel. And I'll call for this diagram. So this diagram, okay. So 4 blocks of the elements. And I also attached the real periodic chart to help us to realize what kind of electron configuration we can have at the beginning and end of some of those blocks. Like, for example, S block. There are only 2 groups, NS1 and NS2. For P group, for P block, we start with NP1, we end with NP6. All right, with that in mind, we can go ahead to write the full electron configuration of nickel. Nickel is the number 28 element, which is probably somewhere right here. And here is where the nickel is. So it's number 28 element. Because atom is neutral, so the number of electrons for nickel in its atom is also 28. And again, as we start from 1s all the way to the end, we hit 1s2. So that is why we write 1s2 to say we hit the end of the first period. Remember, nickel is in the 4th period. We need to keep going down. But for 1s2, we remind ourselves now we hit a helium. It's not there yet. So we go ahead, hit the end of a 2s block. That would be which element? Be, beryllium. As you can see right here, it's beryllium. As we hit the end of a 2p block, that would be 2p6. That is what the neon is. And again, remember, nickel's right over here, right? So nickel's right over here. And we keep going down. So at the end of a 3s, this is 3s2. Which element is that? Magnesium, Mg. And as we hit the end of a 3p block, 3p6, that makes argon. At the end of a 4s, we have calcium. That's a 4s2. And just where is the nickel at in this 3D block? 1, 2, 3, 4, 5, 6, 7, 8. It is the 8th element in the 3D block, meaning 3D 8. This is the full electron configuration of nickel. So we just keep on going to hit the end of each block by keep going down, and we write up the electron configuration at the end of each block, and then we can compile them all together so that we can have the electron configuration of the element. And by the way, we also need to hit the element itself. And it may not be the end of the block, so we just have to count just how many electrons that element should have in its atom for this particular subshell. Like a nickel is the 8th element in the 3D subshell, so that means 3D block, so that means 8 electrons in the 3D subshell. That is the one approach, the approach I prefer myself as a chemistry undergraduate student. But there's another approach, writing electron configuration, the one I preferred when I was in high school. I was good at chemistry, so that is why I chose chemistry as my major in college. Before we talk about that approach, I'd like to go through some numbers so that we can have a better understanding about the number of orbitals or the capacity of electrons for some subshells. For example, S subshell, 1 orbital, 2 electrons as its capacity. P, 3 orbitals, 6 electrons. So how do we know the number of orbitals for each subshell? Consecutive odd numbers, 1, 3, 5, 7 for S, P, D, F. Then we multiply those odd number by 2 to become the electron capacity for these subshells, 2, 6, 10, 14. Now let's introduce another way to write electron configuration, which is we call as off-ball diagram. To write up an off-ball diagram, first we build up stairs. Why stairs to begin with? Because we're going to set up the x-axis, the horizontal one, with a various value of L's. So the most on the left will be 0, next 1, and followed by 2 and 3 for each column. For the rows, that would be the n value from top down, n equals to 1 all the way down to n equals to 7. And what we're going to do is play the combination. Now let's see what kind of combination we have in a space that's above that stair lines. So for example, if we want to take a look at the combination for this position, n equals to 1, L equals to 1. If L equals to 1, we understand that's 1p, right? So that space would be 1p, and n equals to 1, L equals to 2, that would be 1d, n equals to 1, L equals to 2, that would be 1f. And then we can fill out the rest right here. And I'd like to remind you, if n equals to 1, L cannot be 1 or 2 or 3, because that is against the rule for quantum numbers. And it has turned out all these combination of n and L in red are not allowed. So that is the reason why we build up stairs, because anything above are not allowed according to quantum chemistry. When we play the combination of n and L together. And underneath the stairs are actually allowed. So that is why we have 1, 0, 0 can be S, so we have 1S. And since L equals to 0 in this entire column, so we have 1S all the way down to 7S, 2p all the way down to 6p, 3d to 6d, and 4f, 5f. And the order in filling orbitals is always going to start from the corner of each stairs. Okay, so I'm going to change it a different color here. So I'm going to change that to the purple color for you to see. We start with the corner. So the first corner is right here. So we draw the corner diagonally when it hit 1s. So this is the first orbital for us to fill, or first subshell for us to fill. When it's done, nothing else is left. We're looking for the second corner right over here, and hit this diagonally. So that's going to be 2s. Nothing else for the arrow to hit. Go back, looking for the third corner. Hit it so that we have 2p and 3s. Once done, move on to another corner. That would be 3p, 4s. Move to the next corner. 3d, 4p, 5s. Move to the next corner. That would be 4d, 5p, 6s. And from this corner, 4f, 5d, 6p, 7s. And if there are still more electrons to fill, we go to the last corner that we have here. Try to fill in 5f, 6d, and of course there's going to be 7p because this is where our last element is at. So let's have to fill 7p. That is the end of our periodic table. So we find our first corner, go downwards to hit whatever the subshell is. That would be our first. And we keep on going until we fill out all the electrons using this order. Okay, so here I make 7p in red, so that's easier for us to follow that 7p is listed after 60 to fill electrons. Now we have an entire periodic table with the electron configuration all filled out. Okay, so here, we have a group number 1A to A, 3A all the way to 8A, and we have a 3B to 2B with 8B, so 3 columns element in 8B. And we got 4 different blocks. As you can see, this is what we call S block, P block, D block, and F block. And we understand that each row indicates the different principal quantum number. So this is how we organize this periodic table. And we explain why those elements in this particular position using the concept of electron configuration. And how do we get the electron configuration for the element? So the electrons in the element, a set of 4 quantum numbers for each electron. So that is why we have to understand chapter 6 before we understand chapter 7. So once we understand electron configuration and how electron configuration apply to the periodic table, so a lot of things become crystal clear. So for example, elements in the same group. Those elements must have the same outer electron configuration that results in similar chemical properties. And also we realize the number of group A actually tells us just how many electrons in the principal shell with the highest n. And soon we'll find out the principal shell with the highest n is what we call the valence shell. Elements in the second or in the same period actually will have the same outermost shell. For example, elements in the 4th period that must have at least 1 electron in any subshell of the 4th principal shell, or in the 4th period principal shell. So like potassium 4s1, then calcium 4s2, and for the rest of the elements it's either 4s1 or 4s2, and for the rest of the elements in the P block in the 4th period, here goes for the 4p. So they must have at least 1 electron in the 4th principal shell. So that is how we find out elements in the same period. That explains, remember, what we talked about in chapter 2. We said when we have this, say, don't worry, we'll explain that later. So this is how we explain it now. Speaking of a category of electrons, we divide electrons in two groups, one called inner electrons or core electrons. Those electrons are actually in a much lower energy level, so they do not affect chemistry. It is the valence electron that determines the chemical properties of the elements, especially main group elements. The valence electrons are the electrons in outermost principal shell. So that's why we said outermost electron. Why we call them valence electron? Because in history, people find out that there's a certain group of electrons that becomes more important or more value than the rest of the electrons. So they call that group of electrons the valence electrons, and it has turned out, according to our theory, those are the electrons that are located in the outermost principal shell, the principal shell with the highest N. The number of valence electrons can be calculated for any main group element. That would be the number of electrons in the highest S and P together, which is also equal to the main group. So the main group, the group number. Now, it's time for us to have some exercise. So here we are about to give a full and condensed electron configuration, as well as a partial orbital diagram showing the valence electrons for main group elements. We got 3 atoms or element to write about. And I believe that we have done the nickel in our first problem. And the full electron configuration for nickel is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. When we write up the condensed electron configuration, we understand that we can take care of up to 3p6. Okay, those electrons up to 3p6. And the element with the electron configuration of 3p6 is, of course, argon. So the condensed electron configuration would be argon core 4s2 3d8. Does that mean that nickel got the 10 valence electrons? No. Things become a lot more complicated. So that's beyond our scope of general chemistry. In general chemistry, we pretty much focus on the main group elements. As for partial orbital diagram, so we're going to focus on the 4s, 3d, and 4p, even though we do not have any electrons in the 4p subshell. And 4s2 here, so that's why we got 2 electrons up and down in the block in the subshell for 4s. And the first 5 electrons in this 3d8 will occupy every 3d orbital. I just want to point that out. And the 3 extra electrons, 3 more electrons will have those 3 paired. So we got the 3 paired orbitals with the 2 lone pair electrons left. That is the orbital diagram or partial orbital diagram for the nickel. Now let's work on SR called strontium. Strontium is the number 38 element. So here I'd like to use off-ball diagram to help us to write up the electron configuration for this element. First thing I'd like you guys to know, strontium is a neutral atom. Atomic number 38 means there are going to be 38 electrons. If we want to use this off-ball diagram, we need to count the number of electrons to make sure that we do not go over. Okay, so remember that what we did. So we start with the corners, right? So this is a corner first. This is our second corner. So this is our third corner and the fourth corner. And probably we're going to end up with the fifth corner. And we're going down. We hit 1s. When we hit 1s, remember, S can hold as many 2 of electrons, so that's going to be 1s2. And there's 2 electrons that we used. And nothing else to hit, so we go back, starting with the second corner, going down. We hit 2s, and again, 2s2, 2 more electrons. Nothing else to hit, go back, start with the third corner, hit the 2p and 3s. 2p, that will be 2p6, 6 more electrons. And 3s, again, that's going to be 3s2 with the 2 electrons. And as we count now, so that's 2, 4, 10, 12. Okay, so total 38 electrons. So we're still quite far away writing electron configuration. So going back with another corner, we hit 3p, and 4s. 3p will have 6 electrons, and 4s will have 2 electrons. Okay, so 3p6 and 4s2 as its electron configuration. And as we go back again, that is going to be 3d, 4p, and 5s. 3d, 3d10, so that's 10 electrons. 4p, 4p6, that's a 6 electrons. And 5s, 5s2, that's 2 electrons. Okay, so I think we are probably have enough electrons to fill out. So let's count. 2, 4, 10, 12, 18, 20, 30, 36, 38. Okay, so we're done. So this 1s2 all the way up to 5s2 will be the full electron configuration of strontium. Speaking of condensed electron configuration, we can take care of electrons up to 4p6. Remember, for each period, it ends with np6, right? So we can take care of electrons all the way up to 4p6. Which element has such electron configuration 4p6? Krypton. So the condensed electron configuration for strontium becomes much simple. So krypton core is a 5s2. So that is the reason why we prefer the condensed electron configuration over the full electron configuration, because all we need in chemistry is to investigate the electron configuration for valence shell, the outermost shell. So we just take the rest of the electrons, consider them as core electrons, replace them by some noble gas chemical symbol, and so that we can leave those electrons out for study. As this orbital diagram, there's the 5s orbital diagram with 2 electrons filled. We are running out of space for polonium PO, which is number 84 element. So here in the new slide, we're going to work on that element. So here, the approach here is I'm going to write electron configuration using periodical chart. Polonium is number 84 element. So that's where we start to see, this is where we see the polonium. It is way at the bottom of this periodic table. So that means that's going to be a long one for the electron configuration. Remember, this is where we start, right? So we start off the first period, hit the end of that period, we call it 1s2. And as we move to the beryllium, that will be 2s2. As we hit argon, that will be 2p6. Again, moving down to the third period, at the magnesium, Mg, that would be 3s2. Ar, that would be 3p6. We're not there yet. When we get to the calcium, Ca, that will be 4s2. Now we are in the territory of D block. From scandium all the way to zinc, that will be 3d10. Remember, N-1d. From Ga to Kr, krypton, that will be 4p6. Moving on to the fifth period, Sr, that will be 5s2. At the end of the D block, so that's what 4d. So for the Cd cadmium, that will be 4d10. And as we hit Xe xenon, that will be 5p6. We're getting close because now we are hitting the sixth period. At the end of S block, that will be 6s2. And then remember, we're in the inner transition block, the F block. As we hit the end of this F block, remember that is a 4F N-2. At the end, there will be 4F14. Going back, as we finish the D block, that will be 5D10 for polonium. That is the number 1, 2, 3, 4, the fourth element in 6p block. Make it 6p4. That is a long electron configuration for polonium. Either way will do the job. Personally, I'd like you guys to understand both approach, both methods, because you can use one to check up the other. All right. As for condensed electron configuration, we're going to take care of pretty much all the electrons up to where? 5p6. 5p6 is what xenon is. So we got the xenon core, 6s2, 4f14, 5d10, 6p4. As an orbital diagram, remember, we are focused on the valence shell, the one with the highest N, right? 4F, fully filled. 5D, fully filled, so we don't have to care that much. It is 4s2, 6s2, 6p4 that we're interested. First 3 electrons in 6p will occupy 3 orbitals of 6p. The fourth got paired. All right, now we put all 3 together. And when we try to write electron configuration, people sometimes intend to flip the order of some of the subshells. For example, in polonium, people will rewrite it in a way so that it starts with a 4F, 5D, and we have a 6 as a 6p altogether. The reason is quite obvious, because 6s, 6p is what we call the valence shell. And the electrons in this shell determines the chemistry of that element we call polonium. And that is not just for the main group element like polonium. The transition metals like a nickel, okay, we can do the same. So we flip, okay, the order of 3D and the 4s for some reasons that is going to be beyond our scope of general chemistry here. But I just want to let you know. So we won't get surprised to see some articles or the references to have 3D8 4s2 as the electron configuration of nickel. As we try to determine the valence electrons for the main group element, we understand that there are only two main group elements, strontium and polonium. And as we count them, so we realize, so there are 2 valence electrons for strontium and totally 6 electrons for polonium. So that is why for strontium it's in the group 2A, polonium is in group 6A. Our third example problem has 2 questions. So first question, we try to figure out which one is the correct electron configuration for cesium. There's a lot of electron configuration for us to look at it. First, I like to have a periodic table that's ready because I'd like to know what is the last electron configuration for cesium. I'm sorry, this periodic table is a little bit small, but here I'd like to show you where the cesium is at. Cesium is right here, the first block in S, the first group in S block. We understand that's going to be NS1. What the value of N? It's 6. So the last electron configuration for cesium is 6s1. With that in mind, we can definitely kick out the choice number 1 and the choice number 4 because they do not end with a 6s1. We know for sure they are wrong. So we do not have to read every electron configuration. We can start to check the last electron configuration for that element according to the periodic table. Remember, we always have a periodic table available in any kind of exam. Okay, so we take our exam in our classroom, we have a periodic table, and if we have to take an exam for this semester at home as for final, and we have a periodic table on your desk. So we always have a periodic table available for us. So once we realize the last electron configuration for cesium is a 6s1, we can definitely eliminate some of the choices. All right, so let me erase. So now that we have 3 answers ending with a 6s1, here's something that I want you guys to learn, because this is some trick that's going to save us a lot of time in answering a question like this, especially in our final. When we look at the choice number 2 here, it is shorter, right? Why is it shorter? Something's missing. I don't care which one's missing, it's definitely wrong. So I don't even bother to take a good look at the choice 3. Now we have 2 choices to select from, and they have the same length. They both have 6s1 at the end, the last piece of electron configuration for cesium. Now we have to check. Okay, starting 1s2, 1s2, 2s2, 2s2, 2p6. Aha. You see 2p4 right here. That makes number 5 the wrong one. So choice 3 is correct. Okay, so let me repeat this one more time as a better approach to choose correct electron configuration for an element. First, we check the last piece of electron configuration for such an element by checking out the location of the element in the periodic table, like a cesium. Cesium is the first element in the S block of the 6th period. That means 6s1. 6s1 must be the end of this period, so the electron configuration for cesium. This way, we can eliminate a couple of choices. With those choices ending with the 6s1, we eliminate the one with shorter length because something is missing. And usually, if we got 2 of those, and we have to compare. So instead of compare 5 choices, we actually compare 2 to get the correct answer. So this is some trick that we can actually use when we take the exam. The next question is identify the element with the electron configuration of a krypton core 5s2-45. There are two methods that we can use to reach the same answer. The method 1, we use the periodic table, right? So where's my krypton at? So this is my krypton. So this is the krypton. And 5s2, which element has a 5s2? So that's strontium. And so that's strontium. 45 meaning the 5th element in that 40 block. So what is the 5th element in this 40 block? So 1, 2, 3, 4, 5. It's Tc. So Tc is our answer. So this is how we can use electron configuration with the periodical chart to get the correct answer. Or we can count the number of electrons because we're dealing with atom, right? So for krypton, so number 36, it has 36 electrons. And we're going to add 7 more because that's going to be 7 more protons. And we have 7 more, so we have 43. And the number 43 elements will be Tc as well. All right, a little bit more exercise. This type of exercise or the question is the most tedious one, like unpaired electrons. Because when we deal with the question with the unpaired electrons, not only do we have to know the electron configuration, in this question it is generous enough to give us electron configuration. What we need to do more is to write an orbital diagram, because we need to use orbital diagram to tell just how many electrons that is not paired. 1s2, so that's 2 electrons in 1s. 2s2, 2 electrons in 2s subshell. We have got a 2p3. How many orbitals do we have in 2p subshell? 3 of those. And remember, this is where we're going to use Hund's rule. Hund's rule tells us 3 electrons will occupy the 3 orbitals with a parallel spin. That means they all pointing up or point down. How many unpaired electrons? Obviously 3 for nitrogen. So next time when you see this type of questions say in the final, be careful. Okay, this question may require more time for you to do so. Okay, you may want to put this question, okay, after you finish the rest, the easier ones. All right, our last exercise will be how many valence electrons does an atom of phosphorus have? The typical method will be write up the electron configuration. We understand the phosphorus is number 15 element, so it has 15 electrons. So 1s2, 2s2, 2p6, 3s2, 3p3. And better yet, we can write directly starting with the neon, because neon is the immediate preceding noble gas as core. So we can write up 3s2, 3p3. And 5 valence electrons. But there's a better approach. The better approach is, where's my phosphorus? If you realize this is what my phosphorus is, what is the group number? Group number indicates the number of valence electrons, as we already discussed. So phosphorus definitely has a 5 valence electron because group number tells us so. So I just want you guys to remember, valence electrons for a main group element is equal to the group number itself. We have spent some time talking about the electron configuration of atoms. Now, let's talk a little bit about the electron configuration of ions. For example, metal. According to what we have understand from previous chapter and the octet rule, now we can come up with a conclusion that the metal will lose electrons. But by how many? This is where we can actually see. So we can write the electron configuration, or especially the valence electron configuration for those elements. So in group 1A, the valence electron configuration will be NS1. For beryllium, NS2. For aluminum, that are going to be 3s2, 3p1. And we understand these are the number of electrons that metal is going to lose. Why? Because after losing those electrons, metal will have this core electrons, same as noble gas element, to be stable. One way to put it, metal elements will lose the valence electrons, pretty much all of them, to have the same electron configuration as its intermediate preceding noble gas element. So here we focus on main group elements. For main group elements, that is always true. So for all the elements in these three groups, okay, particularly in the first two groups, so group 1A, as we turned out, is going to lose that one electron in the 1s subshell, becomes 1 plus. Group 2A, 2 of the electrons in 1s, so that's be 2 plus. For aluminum, however, since we got 2 subshells with a different energy level, aluminum is going to lose electron with the highest energy level first, which is a 3p. So aluminum is going to lose 1 electron from 3p, then both electrons in 3s. So that is the reason why we can make a compound with aluminum plus. So we just make it right in the middle of it. So aluminum can have 2 3s electrons in its shell. And of course, such aluminum compound is not going to be stable. For the nonmetals, We already know that non-metal elements gain enough electrons to have the same electron configuration as noble gas element, which is at the end of the periodic table, at the end of this period. And of course, with the help of electron configuration of these three groups, and we can actually figure out just how many more electrons that the non-metal elements are going to need. For elements in group 7a, NS2, NP5, total 7 electrons already. So all they need is one more electron, become 1 minus as an anion, the charge of an anion. Group 6a, 2 more electrons, so 2 negative. For nitrogen and the phosphorus, that's going to be 3 minus. You may wonder what happened to AS and SB, because they are actually semi-metals or metalloids. So although they can be the anions, just like nitrogen and phosphorus, but they are not as common as these two. So we do not have them in a lot of cases, like AS3 minus or SB3 minus. And as they turn out, they are not stable as the anions. So two statements I want you guys to understand, and I hope that you have already know those two statements, but here we just try to explain those two statements with the electron configurations of those metals and non-metals. All right, as we approach to the last topic of this chapter, I just want you guys to understand this. It is the configuration of valence electrons that determines all properties of the element, especially for a main group element. So that means once we have the electron configuration, so we can, in theory, predict all the physical chemical property of the element. However, with the knowledge of electron configuration, combining the locations of these main group elements in the periodic chart, we can actually predict the periodical trends as the property of these main group elements. There are two factors that can help us to understand the periodical trend of these main group elements. First, nuclear charge. Second, electron configuration of this individual element. For the nuclear charge, so here I just want to use this half periodical chart and for main group element to make a point. As we cross the period from left to the right, for example, okay, the second period, if we cross the period from left to the right, we see the increase of atomic number. We understand atomic number is equal to the number of protons. So we see the increase of number of protons. Once we have more protons in the nucleus, electron will feel a much stronger attraction from the nucleus. And there's going to be some consequence. As we go down the group, for example, from hydrogen down, we start to see more and more core electrons. That's a fill-in between the nucleus and the valence electron. So for example, lithium, 2 electrons fill in. That's core electrons. For sodium, it's going to be 10 core electrons filled in. More the core electrons, the more repulsion that valence electron feels. And those repulsion definitely is going to offset the attraction that comes from the nucleus. Speaking of electron configuration for the element, that will make some individual exceptions. So our first periodical train that we learn here is the nuclear charge. Across the period from left to right, the charge increases, the more attraction the electron will feel from the nucleus, especially the valence electron. Remember, valence electrons are the electrons in outermost shell. Why we are so interested in the outermost shell? Because outermost shell determines the size of the atom. And also, it is that shell, the principal shell, that involves the exchange of the electrons. Core electrons pretty much have nothing to do with the chemistry. It is the valence electrons that have the chemistry of those elements, or determines the chemistry of those elements. And as we go down the group, the nuclear charge decreases. Now let's look at the first application, the atomic size. As we go across the period from left to right, as we can see, the size decrease as the result. Can we actually explain this? Remember, across the period from left to right, the charge increases, right? Because we add more and more protons to it. The charge increases results the stronger attraction. The stronger attraction meaning that the nucleus will hold those valence electrons closer to itself. Once valence electron gets closer to the nucleus, the size gets smaller as a result. So now we understand the size decreases as the nuclear charge increases. As we go across the period from left to right. Down a group, as n increases, the size increases. Why? Because we just put a bunch of electrons as core electrons so that it will repel the valence electron, making it further away from the nucleus. Further away from the nucleus indicates the size of the atom gets larger. And here's an exception of gallium. If you look at the value of the size of the atoms in this group here, oh, I'm sorry, that is not a gallium. That is germanium. So here's a gallium. Okay, remember the pattern or the periodical trend tells us down a group the size increases, right? As we see, the boron is 85, aluminum 143, the size increases a lot. But for gallium, for some reason, the size decreases from 145 down to 135. Why? If you recall, the previous element, the one before gallium, is zinc. The electron configuration of a zinc is 3d10 4s2. We have complete filled 3d subshell. That definitely has something to do with the shrink of atomic size of gallium. The detailed explanation is beyond our scope of Chem 1 class, and I'm going to leave it right here. So for the atomic size, gallium is an exception because the size decreases then increases. All right. Ranking elements in the order of increased size or decreased size is one of the popular exercises for such topic. And I want you guys to get familiar with it because these are some easy questions with no math whatsoever. And I just hope you guys can grab the good score from these questions. So the first question is, we try to rank selenium, bromium, and chlorine. As we check out these three elements using the periodic table, of course, I do not have a periodic table in this lecture, and I just want you to have the periodic table by you so you can see and find out that the selenium and the bromium, they are in the same period. Since they are in the same period, across the period from left to the right, the size decreases, not increases. It decreases because more protons holding the electrons closer to themselves. So the size decreases. Bromium is on the right hand side, so bromium is smaller than the selenium. Selenium also, the bromium is also have the same group with the chlorine. Down the group, the size increases, so that makes chlorine less than bromium in size. So we see the bromium right in the middle, and we can actually rank those three elements in order of increase in size. That means from small to the large. Chlorine is the smallest, selenium is the largest. But also from this exercise, I want you guys to think about the bromine, because the bromine shares something common with either these two elements. Bromine share the same period with selenium. Bromine share the same group with chlorine. As a matter of fact, we can use bromine as a reference to tell which of this chlorine and selenium has either smaller or larger size. That is exactly the technique that we're going to use in our second question. Now we have three elements: iodine, xenon, and barium, Ba. By checking out their positions or locations in the periodic chart, we find out iodine and xenon are in the same period. Xenon is on the right. Xenon has a smaller size because more proton, less the size. Now, let's look at barium. Barium is a metal. And I just want to remind you, metal usually has a much larger size than the nonmetals because they are on the way left, right? So once they are on the left, the size gets larger. And of course, barium is in the period 6, while the other two in the 5th period. In the lower period, make the size even larger. So we have a pretty good idea that the barium should have the largest size of the three. But we just have to find a way to prove it. So how are we going to prove it? barium doesn't share anything common with any of these other two elements. Barium is not in the same period as these two. Barium is not at the same group with any one of these two. So what should we do about it? Like a bromine in our first example here, we can choose something that share one of these two, like same group or same period, with these two different groups of elements. So for example, I'm going to choose a strontium. We realize strontium is in the same period with iodine and xenon. That makes strontium Sr the largest of all three. Xenon is the smallest one. Sr strontium is the largest. But also strontium shares the same group with the barium. Since barium is in the lower group, so barium has larger size, because down the group the size gets larger. With the help of the strontium, we now can actually rank all these three elements. Xenon is the smallest, iodine is in the middle, barium is the largest. Strontium is not the only one that we can use to link the elements in the fifth period with the barium that is in the sixth period. There's another element that we can use to do the same job. I just hope you guys do realize it already. It is the AT-astatine. Because astatine shares the same group with iodine, and it shares the same period with barium. This way, we can come up with the same